Hello, welcome to this video. In this video, let us derive the efficiency for Stirling cycle. Now, if you consider Otto cycle, diesel cycle, they are all internally reversible cycles because I mean to say internally reversible because the expansion and compression processes are reversible. For example, if you get the work in an expansion, same work can be given to the gas and you can bring it back to the initial state. Whereas, the heat addition and heat rejections are external, right. So, they are not reversible in Otto or diesel cycle because in order for heat transfer to be reversible, the temperature difference between the working fluid and the heat source has to be it should not exceed the differential temperature dt. That I mean to say the temperature difference between working fluid and the source should be very minimal. Now, in case of Otto and diesel cycle, this is not going to happen because heat addition and heat rejection process are not externally reversible because there will be a process where during heat addition the temperature does not remain constant. So, it is important for the cycle to be externally reversible also, or you can say that for a cycle to be totally reversible, we must have heat addition and heat rejection at constant temperature. We can see that is why both Otto and diesel cycle have efficiencies lesser than Carnot cycle, because Carnot cycle follows totally reversible cycle. Heat addition and heat rejection also happens at constant temperature. So, it is also externally reversible. So, that is why we have efficiencies of Otto and diesel cycle lesser than Carnot cycle. Now, one more cycle which we are discussing today is Stirling cycle, also has a heat addition and heat rejection happening at constant temperature. Now, Stirling cycle is in the one which is patented by Robert Stirling is rather complicated, and in order to explain that Stirling cycle, we are considering an hypothetical engine, and many of the books also mention that just to make it simple, we are taking an hypothetical case of a piston and cylinder, and we are trying to explain how the cycle works. Okay. The one which is patented is rather complicated. Now, let us consider uh, as an engine which has got one cylinder, two pistons, and there is a regenerator which is fixed. Now, regenerator's work is to store thermal energy. So, you can imagine that regenerator is made up of something like a ceramic mesh or wired mesh, so which is fixed, all right. Now, imagine that there are two pistons like this, and at state 1 we are considering that uh, left side piston is at to the extreme right position. I mean, that is at nearing the ceramic mesh or regenerator, whereas right side piston has all the gas. I mean, the portion here behind this piston has all the gas or working fluid right now. Now, let us supply the heat QH. Now, what is this QH? Now, QH is the amount of heat which is being supplied to the working fluid. Let us say the gas could be air, helium, okay, or hydrogen. Now, the moment we are supplying heat, we want it to be externally reversible. So, heat addition should happen at constant temperature. Now, let me consider that this should move towards right because any heat addition will increase the volume. Okay. Now, this has to be state 2. Now, this state 2 has to be represented in PV and TS diagram as well. Okay. I just tried to represent this in a dotted line. So, this is our state 2. Okay. So, heat addition is happening isothermally. So, let us say initially the volume was here and pressure is here, and we will have pressure dropped and volume increased, and it is happening in a way that it is constant temperature. So, in a PV diagram, constant temperature process would look like this. And we also know that the temperature at which we are operating now, we call it as higher temperature. So, this is T suffix H, okay, 1 to 2. Now, let us consider 2 to 3. Now, I just have to redraw this again so that I can mention 2 to 3. So, I will take it right below here. Now, this is gone. Now, we are here at 2. Okay. Now, volume is constant. Now, this is no longer there. We are at 2, right. So, at constant volume, the piston should move towards left. In the 1 to 2 process, the piston was moving towards right. Now, in 2 to 3, the piston should move towards left, and the left side piston was fixed in the process 1 to 2. Okay. Now, 2 to 3, it should happen so that the volume remains constant. Now, this is the volume of the working fluid. How can we have this piston, the second piston moving towards left and volume is remaining constant? It should pass through this regenerator, and this piston maintaining the same volume should move towards left. That is the idea. So, volume should remain constant, but we are giving away the heat to the regenerator. The working fluid should pass through the regenerator. So, in order to keep it that way, both pistons should maintain the same distance between them, and it should move towards left. So, that means I will try to represent the same in diagram as well. Maybe we will have a dotted line to represent that. So, this will go till here, and at the same time this has to be reaching here. So, that way we are having a constant volume maintained, but the energy is given to a regenerator. So, 2 to 3 can be represented this way, all right, constant volume. So, I will write PV diagram constant volume like this. Now, remember 2 to 3 is a process where heat is given to the regenerator. 2 to 3. Okay. Now, 2 to 3. Now, let us take 3 to 4. Okay. I will just copy this again. Now, I will say that this is not there, this is not there, and this is where our actual piston positions are during state during state 3. This is the actual position of the piston. Okay. So, now this is compression 3 to 4. Now, I can call this as well as 3. I mean during 3 this is true. I mean both pistons have shifted towards left. Now, from 3 to 4 there is a compression and there is a heat rejection. So, maintaining constant temperature. That means we are rejecting heat during this process. We are rejecting heat during this process to a lower temperature reservoir. Let us call it as QL, and the temperature at which this is operating will be TL. Now, piston should move towards right. I mean to say, one piston is fixed, only this piston moves towards right. Okay. So, that means there will be a compression. Now, 3 to 4 is a compression happening at constant temperature, and we are maintaining constant temperature in a way that the moment we start compressing there will be a temperature rise, but we are rejecting an equivalent amount of heat so that the temperature remains constant. So, during this heat is rejected, alright. So, 3 to 4, now this was our 3, now we have moved from 3 to 4, okay. So, 3 to 4. Now, the last one is 4 to 1, 3 to 4 is this. Now, 4 to 1 is, again I will just copy this so that we represent this here. Now, this is no longer there, we are at this position 4, this is what is the actual position of the piston, okay. Now, we should move at constant volume, and that we have discussed. So, that we have discussed means this volume should remain constant, the distance between two pistons should remain constant, and we should move towards right. Now, 4 to 1 is something like this piston has to go to the extreme right, but remember we are recovering energy from the regenerator. So, this piston should move towards right, and this piston should come to the extreme position. So, I will keep this now, I will keep this in dotted line. Now, this will be our final position 4 to 1, 4 to 1, volume remaining constant, okay, volume remaining constant, 4 to 1. Now, during 4 to 1 we are recovering the energy from the regenerator. So, at constant volume, as the gas passes through the regenerator, it gives back the thermal energy which was stored in the regenerator. So, this will be 4 to 1. Now, we can write this something like this is taking energy from here. This process we call it as regeneration. Now, remember 1 to 2 is a process where we are supplying the heat at constant temperature. So, piston goes to the right. Then 2 to 3 constant volume where heat is transferred to the regenerator. So, at constant volume means piston, the distance between two pistons remains same, the volume of the gas remains same, but regenerator takes the energy. So, 2 to 3 is that process where regenerator takes the energy, but the volume remains constant. Now, 3 to 4 is a process where heat is rejected and there is a compression. Now, 4 to 1 is a process again, regenerator gives back that energy and piston should move towards right in such a way that the volume remains constant. So, this way we are having the energy recovered from the regenerator. So, that is the same thing is represented in PV diagram. Now, let us go to the TS diagram. Now, what is TS diagram in I mean the process 1 to 2 constant temperature. So, constant temperature in a TS plot would be definitely a horizontal line. So, we will have 1 to 2 constant temperature, and that is happening at temperature TH. Now, 2 to 3 is a process constant volume. Now, constant volume is represented this way 2 to 3. in a TS plot. Now, similarly 3 to 4 again constant temperature at lower temperature. So, 3 to 4 is again going to be horizontal line. Then again 4 to 1 constant volume. Now, these two are constant volume. Now, this again constant volume, this is lower temperature, TL is equal to constant. So, this will be our plot in a TS diagram. Now, let us derive the efficiency for Stirling cycle. Now, let us start the same way which we did. Efficiency is given by work net divided by heat supplied, alright. Now, work net is heat supplied minus heat rejection divided by heat supplied, or we can say 1 minus QR by QS. Okay. Now, we know that this is where our heat addition is, this is where our heat rejection is, lower temperature, alright. Now, let us write the same here. We know process 1 to 2, okay. In order to get the Q minus W is equal to delta U. Okay. Now, delta U is 0 because for temperature constant process, delta is given by mCV dt and this temperature constant delta U will be 0. So, Q1 to 2 is equal to W1 to 2. Now, what is work transfer equation for a constant temperature process? P1 V1 ln of V2 by V1. So, P1 V1 ln of V final by V initial. But however, I would like to represent it in terms of temperature. So, I will say PV is equal to MRT. So, in place of PV, I will write P1 MRT and the temperature at which we are operating is TH. Okay. And ln of V2 by V1. Okay. Now, actually this is heat transfer, but even if you try to write heat addition or heat supplied QS, it is same. So, no need to worry about the signs. Heat supplied, I mean this is going to be positive answer because V2 is greater than V1. So, I will write QS is equal to MRTH ln of V2 by V1. Similarly, let us go for heat rejection. Now, for heat rejection, we must go for the process. For heat rejection, we must go for the process 3 to 4. So, I will take process 3 to 4, Q minus W is equal to delta U. Q 3 to 4 minus W 3 to 4 is equal to delta U 3 to 4. Okay. Now, Q 3 to 4 is what again? Delta U becomes 0 because temperature constant process. Q 3 to 4 is equal to W 3 to 4. Now, what is this work transfer or heat transfer? P3 V3. So, initial ln of V final, that is V4 by V3, or we can say MRT3. Now, T3 is what? A lower temperature. So, let me write MRTL ln of V4 by V3. And remember, this is where most students go confused, because we are talking about heat transfer. This can be negative also, as we know that this is going to be negative because heat is rejected. But however, you see that why we get negative technically, I mean mathematically you can see that this V4 by V3, ln of V4 by V3. So, V4 is lesser and V3 is higher. So, this will be negative, alright. This will get negative. And remember, we have already used negative sign here for the heat rejection. So, again if you substitute this negative and this negative, it will become positive. So, we must avoid this. So, the moment I use the negative sign for heat rejection there, we should while substituting there it should be positive. So, QR should be substituted positive because already I have used negative for heat rejection, heat supplied minus heat rejection already I have used, alright. So, I will make this positive and say that heat rejection. So, make this positive before substituting it to expression. Let us call this as expression 1. Make this positive because I have already used negative sign there, and substitute in equation 1. So, therefore, QR is equal to, how can we make this positive? Just write this as ln V3 by V4. So, now we have got one more expression, that is for QR. Okay. Now, I think we can go back to equation 1. Substitute this in equation 1. Equation 1 is equal to now 1 minus m r T L ln of V3 by V4 divided by m r T H ln of V2 by V1. So, these two mr and mr cancels out. For a closed system, mass and this gas constant remains same. And remember, these two also will cancel out. The ratio of V3 by V4, the ratio of V3 by V4 and V2 by V1 remains same. Therefore, this also will cancels out, and we will end up with the same equation which we had in our Carnot engine, 1 minus TL by TH. So, therefore, efficiency of Stirling cycle is given by 1 minus TL by TH. Okay. Thank you.